So welcome everyone to the next lecture in our international series of lectures. So today I am very glad to introduce you Professor Vijay Rajesh from Indian Institute of Space Technology and Space Science and Technology in India. And I personally know Rajesh for long years, and he did his PhD in Japan in Yokohama National University, and then continued his postdoc in Kanazawa University, and then did some postdocs in Korea, and then he turned back to India for his present position. So he's basically a petrologist, but of course he is you can as you see from his title, his recent work is on Martian analogues and how we can use the petrological information to understand extraterrestrial bodies and like that. So it's my pleasure to introduce Rajesh. Rajesh, can you come forward and give a lecture? Thank you very much for agreeing to give a lecture. That's also very we are so delighted. Thank you.
Thank you, Professor Satish, for the nice introduction. So first of all, I would like to thank Professor Satish and other organizers and coordinators of this program for giving me this opportunity to deliver a lecture on this particular series of online series of lecture and this particular program also. So hi, all of you. Yeah, okay. Thank you. So it's Indian time, it's noon here. So good afternoon, all of you. Okay. So the title of my today's talk is Planetary Exploration and Terrestrial Analogues. Okay. So you might have heard a lot of talks on geology. Okay. So in my case, as Professor Satish mentioned, I was a petrologist. Okay. So now I use that petrological and various geological concepts. Okay, to understand the various geological aspects of terrestrial planets, and I am also using some of that Earth-based analog studies to understand some aspects of, like say, Moon, Mars, etc. Okay, so the talk is actually divided into three parts. Okay, so I'll giving more focus to our nearest body, that is our Earth's moon. Okay, so then we will go to some interesting geological aspects of Mars, and after that, like, I will show you how these terrestrial analogues can be used for planetary exploration. So that's the outline of my today's talk. So the major focus of today's talk is on planetary geosciences. So by definition, it is also known as astrogeology or exogeology. It's a planetary science discipline concerned with the geology of celestial bodies such as the planets, their moons, then asteroids, comets, and meteorites. Okay. So the various research areas under this category are like, so we can understand the surface processes, its morphological features, then mineralogy and petrology, chronology, tectonics, the crater morphology. Okay, so the impact craters present on other terrestrial planets are like highly important to understand its various geological features. Then geology of permanently shadowed regions. I will come to that little later. Then the habitable environments, if any. Okay, so this particular aspect has importance on astrobiological point of view also. And for that, like, we will focus on Mars. Okay, so as mentioned to you previously, the focus of today's talk, it is on the significance of geological concepts or theories to understand the origin and evolution of Moon and Mars, and also that planetary analogues or that terrestrial analogues. Tira, is that fine? Audio?
Yes, sir, it is fine.
Okay. So in planetary geosciences, like, let us see what are the sources of our data, or what basis we can study that other planetary bodies. Okay, so most important aspect is the remote sensing based studies, that is the orbiter missions. Yeah. Then we can have like studies like in situ studies, which includes rover, lander, and that manned missions are also there. Then if you are having meteorites from other planetary bodies or from asteroids, etc. Okay, so we can study those bodies or those materials. Okay, so we can have some understanding regarding its formation mechanism, and we can extrapolate those studies to understand like various features of other terrestrial planets also. Okay, then we can have that sample return missions. Okay, so you all know that like from Japanese mission, like okay, Hayabusa. Okay, so it has bought samples from asteroids. Okay, so then Luna missions, Apollo missions, etc. Okay, recently China also chunky missions were there. Okay, so to bring that sample from other planetary bodies. Okay, so through that also, like we can have some studies using the sample return missions. Then another important aspect is like identifying similar materials on Earth, and we can use we can study a lot in various aspects, and we can use those results to understand that the various geological aspects of other planetary bodies also. Okay, so now let us move to the terrestrial planet interior. Okay, so you all know that like the various bodies under the terrestrial planet category. So we have terrestrial planets and Jovian planets are there. Okay, so you can notice that we have Earth, Venus, Mars, Mercury, and Moon. So there are some similarities and dissimilarities also there. Like let us focus on that similarities. So if you're looking at all these bodies along with our Moon, okay, so that's the natural satellite of our Earth, you can notice that they are having a similar type of internal structure. So if you are taking our Earth, it's having a core, then mantle, and crust is also there. So similar type of that layered structure is present on other terrestrial bodies also. Okay, and all these bodies, they are made up of rocky or metallic phases. Okay, so because of that, we call these as the terrestrial planets or like Earth-like planets. So then coming to its dissimilarities, you can notice that like the proportion of core of Mercury is quite high when compared to its crust and mantle. Okay, but if you are taking our Moon, you can notice that the proportion of core is very small when compared to mantle and crust. So these type of like dissimilarities are also there. But the interesting aspect is that applying what we have learned about the Earth's interior, okay, so we can use those concepts to understand other planetary bodies. Like so we can study about that internal structure, then internal composition, etc. And also like these type of studies will let us know like what are that surface features or surface morphology, evolution, etc. So now coming to like after a formation of a particular body, like then shaping up will take place. Okay, so those shaping up includes endogenic processes and exogenic processes. The endogenic processes include like those processes which are taking place internally, and exogenic it will be taking place externally. Like okay, so here you can notice that. So I listed out some of those important activities, like which includes the volcanism and tectonics. Okay, so we can group them as endogenic category. So in that planetary geosciences, we consider this volcanism, which is representative of all those igneous processes. Okay, so it includes some of the plutonic activities also. Okay, so then tectonics, you all know that, like, okay, so because of a plate movement, and if it is on other planetary bodies, we consider it as like a single plate body, and those stresses or the tectonic activities which are taking place within that particular body, we consider here. Okay, so that tectonics and volcanism, okay, so they are part of endogenic processes. Then erosional activity and impact cratering. So this impact cratering is one among that important aspect. Like, okay, so once impactor will come, hit the planetary surface, okay, so we can have formation of impact craters. It has like a lot of significance there. Then erosional activities means, you know that in the case of our Earth, we have like dynamic agents like water, wind, and ice are there. Okay, so it will continuously interact with our Earth's surface. Okay, so lot of changes will take place. But if you are into Moon or Mars, like okay, or let us take Moon. Okay, so it is having a very thin atmosphere, and there is no sort of dynamic interaction between atmosphere and that lunar surface. Okay, so because of that, like that acting off of these agents are in various scales on other planetary bodies. Okay, so now let us take the Moon and Mars. Like, okay, so the significant aspects of Moon are that it's our closest neighbor. So we have some evidence for water ice deposits and various mineral resources on Moon. And also in future, we can consider Moon as an interplanetary launch site. Okay, suppose like we plan to go to Mars. Okay, so we can have like moon as a transit station. Okay, so we can have a refueling taking place from moon, and then we can proceed to Mars. Like, okay, so that's known as that interplanetary launch site. And if you're taking Mars, like it's the nearest planet to our Earth, okay, it has diverse geological processes similar to our Earth. Okay, then evidence for past flowing water was there, and it still has a lot of ice or glaciers are there. Okay, and also because of all these aspects, planetary scientists, they consider Mars as a potential site for future human colonization. So these are some of that salient science aspects of Moon and Mars. Yeah. Now let us come to a comparison between our Earth and Moon, especially the geological activities. Okay, so if you are taking like Earth as a mentioned to you previously, we have like a active interaction between atmosphere and the surface of the Earth are taking place due to various geological agents. Like so, we have active wind or water erosion. Okay, so we have like impact craters are there, but if you are counting that number of impact craters between Earth and Moon, you can notice that large number of impact craters are present in the case of our Earth's moon. Okay, so few craters are there and lot of craters are there. Then in the case of our Earth, active volcanoes there, still we have like because of plate movements or intraplate activities. Okay, so we can have formation of active volcanoes, but in the case of Moon, like till now scientists consider that it is a dead unit or a passive unit. Okay, so we do not have much evidence for recent active volcanoes. Then we have earthquakes. Okay, so due to tectonic activities, and in the case of our Moon, we can have like small moonquakes are there. Then active magnetic field, and there is no active magnetic field on Moon. Then plate tectonic processes were there on Earth. It is still operating, and no plate tectonic processes. And most important aspect, if you are taking Earth, like we have lot of liquid water at the surface. Okay, so this matters a lot. And there is no liquid water, but there are reports of like water ice at the poles, okay, and in permanently shadowed regions. Yeah. So because of all these aspects, we can have like a summary, like Earth, it is still geologically active, and Moon geologically inactive. Okay, and in the case of our Earth, like it's known as, or it's considered as younger surface. And in the case of Moon, like we can see that whatever features which have formed during that earlier stages, that is say 4.5 or 4.4 billion years, we can still see those features clearly. Okay, so which means that the surface is relatively surface is very old in the case of our Moon. So now slowly we are moving to various geological features of our Earth's moon. So the moon, like it has a no atmosphere or a very thin atmosphere is there. Okay, so there are advantages and there are disadvantages are there. Okay, so the advantages are that it allows us to see the surface with fine detail. Okay, so from our Earth, using our naked eye, if you are looking at moon, okay, so we can locate or identify lot of geological features on moon. Okay, another advantage is that there is no weathering of the surface by water or storm, etc. Okay, so that is another important aspect of not having atmosphere or a very thin atmosphere. But the disadvantages are that there is no protection from high energy solar particles or cosmic rays. Okay, so if you are planning for a mission to moon, or if you are planning for a colonization to moon, like, okay, so we will be directly exposed to the solar flares. Then there's no plate tectonic processes, but tectonic processes were there in the case of our Earth's moon. Now, there were like various theories or hypotheses put for the formation of our Earth's moon. Because of like a time issue, we are not going into details of all these aspects. There are like a capture theory, fission theory, accretion theory, and giant impact hypothesis, etc. were proposed for the formation of our Earth's moon. But the widely accepted concept is known as the giant impact concept. Like, okay, so we will be focusing more towards that. So this all happened at approximately 4.5 billion years ago. Okay, so at that time, let us consider two bodies. This is like our proto-Earth, okay, and this is a Mars-sized object known as Theia. Okay, so what happened? That Mars-sized object came and hit our proto-Earth. Right? Okay, it was known as Gaia at that time. Okay, so that collision took place, fragmentation took place. Lot of fragments from our Earth has been thrown out. Okay, so then finally what happened? A fraction of that debris, okay, so it has been accreted, okay, and then brought into the gravitational field of our Earth. Like, okay, so that's the way in which the moon has been formed. I will show you one video regarding the formation of our Earth's moon. Okay, you can notice that Tia, it came and hit the surface of the Earth at that particular time. Okay, so fragments were there. Then they got accreted and brought towards the gravitational field of our Earth. Like, okay, so this is the way in which moon has been formed. Now, let us see some of the salient geological features of our Earth's moon. Okay, so this covers that origin and evolution aspects of our Earth's moon. So here you can notice that two different views are there. That is, one is known as the near side view, and the other one, it is known as the far side are there. So if you are taking that bulk moon, the brighter regions, okay, so these are the brighter regions which actually occupies nearly 83% of the surface of the moon. Okay, then the darker regions, they are otherwise known as the Mare regions or the Mare basalts. Okay, is occupies only 17%. So let's see what are this near side and far side view sensitivity. So from our Earth, we can always see this particular view. Okay, so that is known as the near side view, and that other side or other face of the moon, it is not visible to us from our Earth. Okay, so that is known as it is the far side view. Let us see, let us compare what are the features of like near side and far side. So if you are looking at that near side, you can notice that like a lot of brighter regions are there. Okay, so then a huge cluster of the darker regions are there, and then impact craters are also there. Okay, and if you are moving towards that far side region, you can notice that the proportion of that impact craters are more. Then you are having like a less number of darker regions in the far side regions. Okay, and if you are taking that crustal thickness aspect also, there are some variations between the crustal thickness of far side and the near side region. In the case of like the crustal thickness of that near side region, it is 55 to 60 kilometer, and in the far side region, it is approximately 100 kilometer side. So we can define that features. Okay, so based on impact craters, presence of that darker regions, and also the crustal thickness. So we call this as that hemispherical asymmetry of moon. Okay, so that is that the feature difference between near side and far side region. Okay, so that brighter regions, okay, so they are known as the highland regions of the moon. Okay, so this is that primitive crust of our Earth's moon. It is older, formed during 4.49 billion years, and it continued up to say 4.2 or 4.3 billion years old. Okay, so that Mare regions, it is known as the younger regions of the moon. It is having like 3 to say 1 billion year old, and you can notice that it is having less number of craters when compared to the highland regions. Then there are other important features like rays are there. Okay, so that I'll discuss later. Then rills are also there. Those are simply known as the lava tubes. So simply these are the geological features of our Earth's moon. We are having highland, we are having that low-lying regions or the darker regions or the Mare regions. Then large number of impact craters there, and also like rays, rills, etc. were there. So now, like before moving to other aspects, we can have some idea regarding what are the various minerals and rocks present in our lunar surface. So this is actually the mapping of moon. It is like a full disk image of our Earth's moon. You can see like a lot of color combinations are there. So red and purple regions are there, then blue, then pink regions are also there. So you have seen like this particular view, and again like that color coded mapping of that lunar surface is also there. So here you can notice that the majority of that region, it is 83% of that particular region, it is covered by either this one red or regions are there. Okay, so now let us see what are those important minerals. Like, okay, since it is known as that brighter region, you can notice that it is made up of brighter minerals like plagioclase feldspar. Okay, so the important plagioclase feldspar is anorthite here. You all know the composition of that anorthite. Okay, and if you are having like say 90% or more of anorthite content, that particular rock is anorthosite. Okay, so you can notice that the highland region, it is composed of anorthosite. Then with a less proportion of pyroxene and olivine are there. Okay, and when you are moving towards the mafic region, you can notice that abundance of pyroxene, olivine, and then some iron titanium oxides are also there. That is known as that ilmenite is there. Okay, along with some calcium rich plagioclase is there. So using these 3 or 4 minerals, like we can explain that petrology or petrogenesis of our Earth's moon. Okay, so I'll be discussing those aspects in the subsequent slide. So let us see how those highland regions of moon are formed. Okay, so I mentioned that is that oldest crust or the primitive crust of our Earth's moon. So immediately after the formation of our Earth's moon, you can notice that it was a hot molten in nature. So we all know that melt with course of time, okay, cooling will take place, formation of crystals will be there. So in this particular case, that the lunar magma ocean concept or the global lunar magma ocean concept that explains the formation of the primitive crust of the Earth's moon. So here you can notice that this is the unmelted region, and because of various heat sources at the initial time, so it has a huge magma ocean was there. So with course of time, what happened, like a solidification took place and crystallization of three important phases. Okay, so for today's purpose, we are focusing on only three minerals, that is the plagioclase, olivine, and pyroxene. So olivine and pyroxene, it is having iron and magnesium in its structure, and plagioclase, it is having calcium, aluminum, silicon along with oxygen are there. So because of, you know that from a particular magma, if you are having co-crystallization of plagioclase, olivine, and pyroxene, and following that Bowen's reaction principle, okay, so we can have that co-crystallization of these two units are there. So what will happen to olivine and pyroxene? Since it's a heavier or denser, it will settle towards the bottom, and that plagioclase feldspar, what happened? It has floated towards the top. Okay, so you know the composition of plagioclase feldspar, it is calcium, aluminum rich, and it is lighter. Okay, and continuous accumulation of that plagioclase towards the top has created a thick crust of moon, and that is that primitive crust or the highland crust of our Earth's moon. And we can easily define the mantle regions of our Earth's moon, that is that pyroxene and olivine, it has actually sunk towards the bottom. You have a mantle with olivine and pyroxene. Okay, so we explained that crustal part, that is highland region, and that mantle part, it is olivine and pyroxene rich regions are there. And in between, that fractionation sequence continued, and there is a layer known as creep or high heat producing regions. That creep means KRWP. Okay, so it is potassium, rare earth, and phosphorus enriched regions are there in between. Okay, so I hope the concept is clear. So this is the mechanism, that is the global lunar magma ocean concept that explains the formation of anorthositic crust on the moon. So now we have to consider that towards the top we are having anorthosite, and towards the mantle part we are having olivine and pyroxenes are there, and also internally heat producing elements are so there. So based upon that fundamental principles of petrology, okay, heating, melting, etc. will take place, and once melt forms, what will happen? It will try to come out. So we will explain those processes later, and those processes, those petrologic processes, further explains the formation of these lunar darker regions. Now, before moving towards that lunar darker regions, let us see the general features of lunar highland region, that is that anorthositic region. I will show you one video regarding that one. So you can notice that this is a highland region, or that earlier formed crust of our Earth's moon. So it is not having a smoother topography. You can notice that it is a rough and rough terrain, is rough and rugged type of terrain is there, with lot of impact craters are there. Okay. So that is that general feature of that highland region, which has been formed at 4.45 or 4.49 billion years ago. So all these regions, like, okay, so they are known as the highland region. And in the far side also, we are having like a huge concentration of highland materials are there. Okay, so now let us see how those mare regions are formed, okay, or that darker regions. So in order to have the formation of that darker regions, we should understand the role of impact cratering processes. Okay, so there is some role of impact activity. What will happen, like when impactor, it's coming up with very high velocity, okay, and once it hits the planetary surface, there will be effect of pressure, effect of temperature will be there. So because of that pressure effect, there will be formation of shock wave, and that will penetrate towards the deeper side of a planetary body. So the shock waves, it will create some fractures, and if those fractures can reach up to partially molten regions, okay, what will happen? Those melts, already it will be looking for some opportunity to migrate towards the top. Now, because of that impact activity, it got a fracture, and through which those melt can come, and reach to the surface. So that's the way in which that mare regions have been formed. So I will show you some of that important aspects of that impact cratering processes. Yeah. Okay. So here you can notice that impactor came, hit the planetary surface. Okay. So a lot of ejecta materials have been thrown out from that one. So that is one advantage. Because of that impact activity, we are having like a formation of ejecta materials will be there. So to some part of the time, what will happen? These ejecta materials will towards the atmosphere. Okay. And once it settles its velocity, what will happen? This will come and hit the planetary surface itself. So due to that external impactor activity, there will be formation of a crater, and that particular crater is known as a primary crater. You can also have a secondary crater surrounding the primary crater. Okay, so that has actually been formed due to these secondary ejecta materials. Okay, so we can see those processes here. Okay, so this is the primary impact crater. And here also you can notice that those materials, it is falling down. Okay, you can see the formation of subsequent craters. They are known as the secondary impact craters are there. So which means that surrounding a primary crater, you can have like a large cluster of secondary craters will be there. So now let us move towards that internal part of those impact craters. Okay, so the advantage is that especially in planetary geoscience, okay, so from through our naked eye or through orbit remote sensing, okay, so we cannot, if the surface is smooth, okay, so we cannot see what are the materials towards the deeper side. But if impact craters are there, those are the ideal sites, okay, that exposes the deeper part of a particular planet. Now here we are going towards the deeper region of that particular planet. So here this is the particular crater. Okay, so this is that wall region, and here you can notice that inner wall, there are some brighter regions are there, shadow regions are also there. So the shadow means it is due to that illumination activity. So there are some regions on moon or planetary bodies where sunlight cannot reach or penetrate at that particular region. So those regions are known as the permanently shadowed regions. And since it is inside a particular crater, we call it as a permanently shadowed crater, or permanently shadowed regions are there. Okay, so these permanently shadowed regions have some advantages. I will discuss that advantages little later. Then inner walls, here you can notice that it's a brighter regions are so there. So brighter regions means sunlight can illuminate this particular region, and here it cannot illuminate. Okay. Okay, so this is actually that walled region, so that internal regions of that moon are exposed over here. We can have direct measurements here, so that internal chemistry or composition will be known to us. Yeah. Okay, so we will see some other aspects of impact crater. Okay, so here you can notice that this is a crater, and surrounding that crater, lot of brighter features are there. So if brighter features are there, those type of craters are known as rays or rayed crater. Okay, so why these brighter features are there, which means that like they have been exposed to sunlight for a minimum time. And if you are noticing like a darker feature surrounding a crater, which indicates that it has been exposed to solar flares for quite long time. So same as that our sedimentology stratigraphic principles, like in the case of moon and other planetary bodies also, we have some technique for relative age dating purposes. Okay, so if you are having that brighter craters are there, we can consider those particular region or surface as younger regions, and if darker features are there surrounding a crater, we can consider it as older craters. Okay, so that's a sort of relative age dating. I hope it is clear to all of you. So here you can notice that brighter features are there. Those are known as that rayed craters are there. See, these are like darker features are there. Those are obliterated or older crater. Here, no brighter features are there. Because of that, this particular region is known as that older are there. Now, brighter features are there. Those are the young craters. Okay. And in the case of our Earth, like so we said that like there is no dynamic interaction with atmospheric agents. Okay, so we in general consider that there not be any type of mass movements taking place in case of moon. But in the case of moon also there were mass movements. Okay, so because of like this one gravity activities, like okay, and for that purpose also the craters are the ideal sites. What will happen if some trigger is there? migration of materials, especially that ejecta materials will take place along that crater wall, and it will move towards the floor of that particular crater. So we can consider this as that landslide activity is taking place in the case of our Earth's moon. See, the mass movements are taking place over here. Now, let us see how those mare regions are formed. Okay, so for that, this particular aspect is important. So because of impact activity, you can notice that shock waves will be developed, and that shock waves, it can penetrate towards the deeper side. It is not necessary that all shock waves will penetrate to the region where you are having partially molten materials are there. Now, you know that towards the internal region, we are having olivine and pyroxene, which is mafic or ultramafic in nature, and melting of that melting of that ultramafic materials can give rise to mafic materials, okay, or mafic magma or mafic melt will be there. And there will be several pockets of that partial melts will be there. And once through that shock wave, if the fracture can penetrate towards the deeper side, what will happen? Already this melt will be looking for some opportunity to come out. Okay, so through this fracture, this melt will migrate, it will come and occupy this particular crater, so that that crater will get filled with these mafic materials will be there. Okay, and what will be the color of that particular magma? It will be darker in nature. So that is why you are seeing that darker features over here. See. Okay, so let us see how those darker features are formed in the case of our Earth's moon. See, you are having primary craters are there. Okay. And now you can notice that that melt will come and occupy these impact craters, I can see. Okay, so what are the features you have observed over here? So here you can notice that this is a mafic magma. We can say that this is a basaltic magma. Okay, so it came and reached to the surface. Okay, it's a sort of volcanism taking place in the case of our Earth's moon, and cooling of this can give rise to the mare materials or the mare basalts. And here you can notice that after filling that particular crater, there is an overflow is taking place, so that you can see that a tubular type of or a channel of lava is there. So we call it as lava tube or rills. Okay, rills or rills. Okay, so these are other important features of our Earth's moon. This is a lava tube. Okay, so overflowing of that particular lava is taking place. Okay. Now, you can also notice that in the case of anorthositic highland region, we observe that that particular region is like a rough or rugged terrain was there. But here, because of that volcanic activity, notice that this is a relatively smoother when compared to that undulated highland regions. See. Okay, so this has important advantages if you are thinking of that landing missions to moon. So you can notice that like nicely we have explained using our geological, petrological concepts regarding the formation of highland regions of our Earth's moon and the mare regions or the low-lying regions of our Earth's moon. Now let us see some of that other important aspects of these features. Like, okay, so here we have explained the formation of highland regions and the mare regions also. Okay, so now coming to that impact craters, like we can have like a simple like a diverse morphology of impact craters can be there. Okay, so we can have like a minor pit-sized craters be there, then simple craters, that means a simple bowl-shaped features be there. Sometimes what will happen, like a rebounding mechanism will take place in order to adjust the isostatic equilibrium. Okay, so that there will be development of central peaks will be there. These again, those are the deeper materials coming towards the surface. Okay, so we will get some idea regarding the composition of materials present towards the deeper side. Again, when that impact activity is in intensive stage, you can have formation of multi-ring basins are also there. Okay, so these are the significance. Okay, so already I have mentioned some of the important aspects of impact craters. Okay, so here you can notice that like this is one case of impact crater. This is the wall region. This is the floor region. Then this is the raised rim or that outside region of impact craters are there. Okay, and this is that Barringer crater in Arizona. Here you can notice that this is the surface like where that deeper regions are hidden. Okay, but if you are looking at that impact crater over here, we can see what are the materials present towards the deeper side. So this has a lot of advantages in the planetary science context. Okay, so the advantages are that we can understand the deeper region of a particular planet, otherwise not exposed, and also it is important in relative age dating of our terrestrial planets other than our Earth. Now, here I will show you one simple example. If you are closely looking at here, okay, so this is one image from NASA. You can see some that lobe type of ejecta blankets are present over here. Let us see how those type of ejecta blankets are there, and based upon some simple concepts, okay, so how can we come to a major conclusion regarding the process of these particular regions. This is from Mars. So scientists have identified similar type of impact craters on Mars, and they consider this as a very good evidence for the presence of past water on Mars. I'll show you some simple video over here. See. So they're throwing a stone in a muddy terrain. Okay, you can notice that splashing effect is taking place over here. So we can correlate that to this particular region. So which indicates that either that particular region was waterlogged at the time of impact activity took place, or subsurface you are having ice was there. So because of that heat released from impact activity, it will melt those icy materials. It will mix with the superficial materials, and you can have a splashing effect of that muddy type of materials will be there. And finally, these type of features will be formed. Okay. So these are some of the clues, because at present the conditions of Mars that are not at all favorable for the presence of liquid water. Okay, but these are some of the evidence to say that once upon a time liquid water was present in the case of Mars. Okay, so now I mentioned that craters, impact craters can also use for relative age dating of a particular planet. So one criteria already we have discussed. If you are having brighter features surrounding one impact crater, we can call it as a red crater or younger crater, and the darker features are there, it is the older crater. Same as that one, in one particular region, if you are having large clusters of craters are there, especially the primary craters, we can consider those regions as older. Okay, and if like a less number of craters are there, like we consider it as the younger regions are there. Okay, so how we can correlate that one? You can notice that this is an older road. Okay, so large number of, it may not be same for different countries, but if you take example of some of the places, you can notice that toward the older roads, okay, you can notice large number of craters are there. Not craters, sorry, the gutters or potholes are there. But if you can notice that recently laid road, okay, you can notice that no craters are there. So using that simple concept, we can say that this is the older one and this is the younger one. Same we can apply to one surface of moon. Here you can notice that large craters are there. That is indicative of older surface, and this particular region, the Mare region, you can notice that less number of craters are there. Because of that, it is considered as younger regions are also there. So this has been modeled, okay, and correlated with the Apollo mission absolute ages also, and scientists have nicely correlated within that acceptable error limits. Okay, so this is one technique to understand the relative age date of other planetary bodies. Now let us see how that data is taking from moon or other planetary surfaces. So in the case of our moon, as I mentioned, plagioclase, pyroxene, olivine, then ilmenite are there. Okay, see, this is that probe, the probing lunar surface. So depending upon that reflectance, absorption, and emittance properties of that materials over here, we will get the data, and that we have to apply suitable correction, atmospheric, terrain, etc. So many corrections are there. After that, we can get some meaningful spectral data. Okay, so which we can interpret for identification of significant elements and then minerals. Okay, so probing. Okay, and we'll be receiving data in that electromagnetic spectral regions. Okay. So now it is probing surface, okay, and emitting absorption and reflectance properties. Okay, so data will be transmitted to the payload, and from the payload it will be transmitted to the data center placed the Earth. Okay, so this is a sort of raw data we're getting, and then up with the suitable correct mechanism. Okay, so we can extract that meaningful data. See, So based upon that absorption parameters, we can have like a different group of elements, iron, calcium, aluminum, etc. And if one particular region you are having higher concentration of calcium, aluminum, etc., we can say that that particular region is of plagioclase. And if higher abundance of plagioclase are there, we can say that anorthosites are present in that particular region. Okay. So now coming to some other aspects of moon. This is that global mineralogy of our Earth's moon. This already I have explained. Okay, so these are purple and blue rich regions. Okay, so they are indicative of iron rich lava flows. So this itself indicates that within that basaltic region, you are having different color codes or color compositions are there. Okay, indicates the diverse composition of basalts present in this particular region. Again, the red and the pink regions, they are indicative of mineral plagioclase. In the same concept is applicable over here. Sometimes it's a pure plagioclase or pure anorthosite. And sometimes what will happen, like with the some component of sodium, that compositional variation will take place. But in any case, like it is mostly composed of anorthite in the highland region. Then these are the rays. Okay, so I have already explained how rays are formed and what are its significance in the case of moon and other terrestrial planets. Then there are formation of impact melts are also there. So here what will happen, that external agent or external impactor along with that superficial materials will melt due to frictional heat, and you can have flow of that impact melts will be there. Okay, so this is another interesting geological features of moon. Then we can also have that landslides, okay, formed in the case of our Earth's moon. See, these are some evidence for landslides present in the case of our moon. Then you all know that how regolith been formed in the case of our Earth. Okay, so these are some of that regolith. Okay, you can see that a footprint of astronaut moon. Okay, so here this indicates that the surface is relatively smoother or it is made up of loose materials are there. So these regoliths are also formed due to that impact activity. Okay, and we have collection of like so many regolith samples, and scientists have identified impact melts from this particular region. So they have identified olivine rich glasses, titanium rich glasses, etc., which will give us some clue regarding what is that internal composition of our Earth's moon. So these are the major geological features. Again, if you are thinking of like resources, okay, so moon also have lot of resources are there. Okay, a major branch of study is also going on in the case of moon and other planetary bodies, that is in situ resource utilization studies. Okay, so how we can extract the materials from there, okay, and how we can utilize it for the purpose there, or how we can bring it back to Earth and we can utilize it for our own purpose. Like, okay, so different categories are there, like regolith, mineral, metal, volatiles, then water, ice, etc. are there. So like if you are taking that solar wind implanted volatiles, you can have like higher concentration of hydrogen and helium are there. Then incompatible trace elements, rare earth elements, etc. are there. Then it also has huge resources of major and minor components. So you can notice that 83% of lunar surface is composed of anorthosite. Okay, so anorthosite is made up of calcium and aluminum. Both we can use as a refractory materials. Then vapor mobilized elements are there. Then siderophile elements are also there. Okay, from that one, a huge volume of water ice. So there in the subsequent session, like we will be focusing more towards the formation of water ice. Okay, now geologists can also play a major role in choosing a landing site there. You can notice that like how we can select a landing site in case of moon or other planetary body also. See how they are probing a particular surface, like, okay, so based upon topography, then if the surface is level or like say undulated surface, that is also important, especially that rover wheel movement is considered. Then temperature of that particular region. Okay, thermal mapping will take place. Okay, then hazard mapping, okay, in various dimensions, like minor hazards, major hazards, etc. will be mapped upon. So then entire surface will be undergone, like a series of imaging will be there. Okay, so this red regions, okay, large rock hazards are there. Okay, so which means that these sites are not suitable for landing purpose. Okay, you can notice that all these this one parameters, they are like geological aspects only, and based upon that, like scientists can identify or demarcate that safe landing site. So here also, like a geologist can play a major role. Okay. Now let us look the previous landing sites on Moon. Okay, so you can notice that like almost like say 90% or 95% of the landing took place in that Mare region, and only like a very few missions attempted to land on that highland region. The reason is that that highland region is rough and rugged, and it is easy for rover wheel movement in a smooth terrain. So which is that Mare regions are there. So you have seen in that particular video, the Mare regions, they are relatively smooth. So that Luna mission, then Apollo missions, etc., they have landed in these particular regions only. Okay, but now technology is getting advanced. Okay, so the planetary scientists, they are aiming to land on other regions, because this covers only 17% of the lunar surface, and that other region covers 83%. So we need more stuff or more materials from this particular region. Okay, so now coming to the water on Moon, like you might have that significant aspect of lunar mission. Okay, so it is on identifying that water on the Moon. So almost the major space agencies like NASA, ISRO, JAXA, ESA, etc., they are actually working on like the water budgeting Moon. So we have again two different categories of water. So water in the sense that it is not liquid water, it is water ice here. And endogenic means it is the water trapped in some of that minerals, especially present in that lattice structure of those minerals. Like, okay, so here also we can categorize like two regions, like exogenic and endogenic. So exogenic, it is like a lunar ice, okay, so deposited by icy comets, etc., which can be observed in the polar regions and the shadowed part of the craters. And why it is preserved over there? Because of that poor illumination conditions. Like, okay, the aspect is that if sunlight cannot penetrate those particular regions, what will happen when ice been deposited over millions of years? It can be preserved as water ice for quite long time. Then we have endogenic water also. So that is known as the hydroxyl ions. So that apatite, etc., the crystals of Mare basalts, okay, it contains water-bearing inclusions. Okay, so that is due to the crystallization of magma. So not only apatite, recently scientists have identified water inclusions in olivine, pyroxene, and plagioclase also. Okay, so that is like endogenic water on Moon. So what are the various sources of polar volatiles, especially the water? Okay, so which includes the contributions from comets, asteroids, interplanetary dust particles, then giant molecular clouds, the Moon itself, and that solar flares. Like we will see some of the aspects. We are not going into all the aspects of one. So this is one significant finding from our own mission. Like okay, you can notice that this is a mapping of lunar surface, and towards the polar region, northern and southern polar regions, you can see the blue colored regions are there. So in those particular regions, like scientists have identified water ice on Moon. So water ice deposits have been identified in these regions of polar lunar polar regions, and it is especially identified on the permanently shadowed regions. So I'll show you some of that significance of water ice deposits in the permanently shadowed region. See, this is one particular crater. Okay, so but we can only see like a 10% of that crater. Okay, 10% of that crater is only illuminated. Okay, so other part it is permanently shadowed. So which means that if some of that ice has been deposited over this particular region, it will be preserved as water ice for quite long time. See, this is actually a mapping of permanently shadowed region on lunar south pole. So you can notice that like it is not a small number. Large areas of that polar regions are covered with permanently shadowed regions. Now let us see what are the importance of that permanently shadowed region. Probably some of you might have read about that Artemis mission, that upcoming mission of NASA. It's actually a landing mission. Okay, so they have actually identified a site over here surrounding this Shackleton crater. Okay, so here also I'll show you some of that important aspects why they have selected that particular region. So this is one sketch of Shackleton crater. So you can notice that dimension 4.2 kilometer deep and 21 meter across. Okay, so and we can compare that crater with our Grand Canyon, and then you can imagine how large was that particular structure. Scientists have identified huge volume of water ice in this particular crater. So the aspect is that a single larger crater having huge volume of water ice. Okay, then you can imagine like other permanently shadowed crater also, how much quantity of water can be present over there. Now, with this concept, we can think about that overall availability of water on moon, and then we can go for that water budgeting and constructive use of water rights. It is not only for human colonization if we are planning, it can also for fueling purposes. We can have like a dissociation of water, we can have that dissociate into hydrogen and oxygen, and we can have that fuel from these dissociated products. Okay, and if you are planning for a mission to Mars, like we can have a transit over here, and then refueling can take place over here. Okay. So that is another aspect. Now, second, what will happen if you are having like solar flares are there? What will happen? It will come interact with the lunar surface. So lunar surface, lot of like silicate minerals are there. Okay, so here it will implant H plus, and it will come hit at the surface, breaking of that molecules will take place, and H plus ions, it will react with the oxygen. You can have formation of OH. Okay, and then it will migrate to the polar regions in the permanently shadowed region. So this is that another source of water present in the case of our Earth's moon. Also, this is I am not going into details of this one, but you can notice that this is an olivine mineral, and scientists have identified a spectral band, that OH absorption band in that particular mineral, which means that that particular olivine in its lattice structure has hydroxyl ion component is there. Okay, so that forward a finding that endogenic water can also be present in the case of moon. So previously scientists considered that all that initial magma of moon was anhydrous. Okay, but because of these type of findings, scientists put forward a model that the magma is hydrous in nature. Like, okay, so a lot of modeling studies were also going on there. Now, another important aspect of moon is that lava tube or rills are there. See, these are the lava tubes. Okay, the buried lava tubes there. So here, you know what is a lava tube. Okay, so internally, if lava movement is there, solidification will take place outside. Okay, and internally, lava can flow. Okay, so once all lava have been withdrawn from that particular structure, what will happen? We will get a hollow structure over here. And here, this is one type such structure in the case of moon. Here you can see the collapsed region, and this is the uncollapsed region is there. So if you are planning for some colonization, we can enter into this particular region, and we can move towards this particular region for shielding from solar flares. So this is also a concept proposed, and many of those planetary scientists who worked on colonization aspect. Okay, so they consider this as a potential site for colonization on moon. Okay, so now I'm going quickly. Okay, with the advancement in technology. Okay, so we are having high resolution images from moon also. So this is a one particular crater which has been imaged by previous mission, but recent missions we image nicely this one, and you can notice that difference between these two craters. Like, okay, so here only minimum features are exposed, and but here you can notice that maximum features were there. So most of our geological interpretations previously were based upon these type of features, and now here you can have like much features were there, so that that evolution or formation mechanism, we can have a better interpretation of that one. Okay, so here also you can see that this is a optical image, and this is that synthetic aperture radar images are there. So here we can take this particular crater. Okay, you cannot see that ejecta blanket over here, but here you can notice that nicely that ejecta blanket have been focused towards this particular side. So based upon that, we can have some inference about that direction of that impact activity and towards which direction that ejecta be moved out. Okay. So now we are getting like a high resolution images. Okay, the craters can be visible very clearly. Then small boulders are also can be imaged. So advantages are that, like if you are having boulder movement, we can track that movement, and we can propose something about that quake activities still taking place in the case of our moon. Yeah. Okay, so now we have technology to have that all type of mineralogical and volatile measurements on moon, so that like in future, if you are having like a very good idea about what are the various minerals, its absorption parameters, etc., so we can have a better interpretation about the formation and evolution of our Earth's moon are there. So this is regarding our geological aspects of our moon. Like in our lab also, like we are working on various aspects of our moon. Like it includes mineralogical studies, then morphological studies, etc., and also that this one terrestrial analogues. Okay, so we use some of the spinel or anorthosite composition to understand some of those aspects of moon also. Okay, again, like see that soil simulants, etc., can also be prepared based on earth-based materials like that. Okay. So do you need like a 1 minute break? Something? Adira,
Sir,
or may I proceed? Like, yeah.
think anything is fine. If you want 1 minute rest, then
So how about our audience? Are they following?
Satish, here there are a few questions, but I think we will discuss. We will take those questions in the end, is it not?
Okay.
Right.
Yeah. Okay. Yeah. Okay.
Yeah. Please
Yeah.
carry on. I
Yeah.
think they
So
are.
let us now move to our red planet Mars. Okay. So now we have from Moon. Okay. So we are moving towards the Mars again. So you can see that full disk view of our Mars. Like, see, there are many geological features are there. So if you are thinking about that, the largest volcano in our solar system, okay, so it is the Olympus Mons present in Mars, and the largest canyon or valley present in our solar system, that is the Valles Marineris. This is also present case of our Mars. Like, okay, so which means that like a lot of geological processes were operated or like still operating, especially that exogenic processes were operating in the case of Mars. So Mars, it is known as a red planet. Okay. Why is it so? Like the simple answer will be lot of iron oxide dust are present in the case of Mars. Like, okay, so we can further think about how these iron dusts are formed. Okay, so we can bring the geology over here. You have like primitive volcanic material over there, and that material underwent lot of weathering activities, which includes the chemical and physical activities. Iron has been released, or iron oxide dust has been released from that one, and it has been deposited on the surface of the Mars. So that's the reason why we consider it as a red planet. Then lot of volcanoes are there, like the largest volcanic structure or the largest volcano, it is present in the case of Mars. Then impact craters and large basins are there. Then a deep system of canyons are also there. And we have a lot of evidence for presence of past water in the case of Mars. So because of that, the planetary scientists consider it as a potential planet for habitable, or like a lot of habitable environments are there, like past and present. Okay, so now moving to major science goals of Mars. Like, okay, so one important aspect is regarding the life. So if you are mentioning about the life, scientists are not looking for a complex life form like us. Okay, so they are looking for any primitive life form that is like unicellular or like a very simple life form. So in order to determine whether Mars has ever supported life in its evolutionary history. Then second aspect, that climatic conditions. Okay, so I will show you some good examples for that. The climatic variations taking place on Mars even recently. Okay, so it is to understand the processes and history of climate on Mars. Then geology, of course, like we are very much interested in that one, like understand the origin and evolution of Mars as a geological system, and combining all these aspects. Okay, so prepare for a human exploration in future. Like, okay, so those are the major important science goals of Mars. Now coming to the topography of Mars. So we nicely explained that geological feature variations between the near side and far side of our Earth's moon. Same as that one. If we are coming towards the Mars, there is some variation between the southern hemisphere and the northern hemisphere. So you can notice in some of these images, okay, so this is the southern hemisphere of Mars, and this is the northern hemisphere of Mars. The northern hemisphere, it is younger, smoother plains are there. If you are applying that crater counting technique, we can notice that this having less number of craters are there. Because of that, planetary scientists consider this as younger region. Okay, then towards the southern hemisphere, you can notice that large number of craters are there. Because of that, it's known as that older crater terrains are there. Then huge impact basins are there, and also tectonic valleys of like thousands of kilometers long are there. Okay, so these are the crust. This also explains the crustal dichotomy of Mars. That is that the difference in the various features, especially the geological features present on the northern hemisphere and southern hemisphere. Though like this is a boundary, we cannot like precisely demarcate that boundary between that northern hemisphere and the southern hemisphere. Okay, so here also another important another topographic image of Mars, like these are the southern hemisphere and this is the northern hemisphere. Okay, you can notice that this is a smoother in nature, less craters are there. Here large number of craters are there, a sort of rough and rugged terrains were there. So many planetary scientists considered that like towards the northern hemisphere, there was a huge ocean. Okay, because like we got many evidence for delta outflow channels, etc. were there. And because of that, they proposed that once upon a time, a mega ocean was there. Case of Mars, like, okay, so they proposed they have some evidence, but we need more evidence to confirm that, okay, once upon a time, that ocean was there on Mars, right? So this is that planetary evolution sequence of Mars, like towards same as our Archean or Precambrian age. So Mars has presence of clay. Okay, when we move to that middle age, that is known as Hesperian, it has sulfates are there, and the Amazonian period, that is that younger or recent period, it is dominated by anhydrous ferric oxides are there. So the significance is that towards the older stage, that is during Noachian period, you are having lot of clays are there. You all know that clay means it needs water for its formation. Okay, so this is one important evidence to say that once upon a time, especially during the earlier stage of Martian evolution, clays were there, and clays are formed at that neutral pH environment. Okay, and towards the middle stage, you can notice that lot of volcanism were there on Mars. Okay, it released lot of gaseous phases to Martian atmosphere. And because of that, that environmental conditions of Mars also has changed. From that neutral environment, it has changed to acidic environment. And that has created or instrumental in developing lot of hydrous sulfate minerals on Mars. So previously, during Noachian stage, it was clay. Now it has moved to that hydrous sulfates like gypsum, jarosite, kieserite, etc. I'm not going to that mineralogical details, but important aspect is that because of that volcanic activity, that environmental conditions have changed, and you have formation of lot of sulfate minerals are there. And towards the younger stage, these activities have been reduced. Previously, scientists considered that this period was anhydrous, but later they got some evidence for like water activity during this period also. Like, so we cannot say that this is the whole period was dry. Okay, towards some part water activity took place over these particular regions are also there. Now, why these hydrous minerals are important in the case of Mars? So we have phyllosilicate, we have hydrous sulfate. Okay, so important aspect is that they could be linked to the missing water on Mars. Okay, and if we are thinking about Earth, like our life, it is like based upon water or like say carbon based life activities, like, okay, so water is essential for life forms, and also based upon this clay and sulfate. Okay, it can give us some clue regarding the environmental conditions on Mars, such as neutral, alkaline, and highly acidic, etc. And if you are taking that Earth-based analog studies, like a lot of microbes can grow on these hydrous sulfates. So important aspect is that if we want to probe on like say astrobiology related activities, we have to probe these hydrous sulfates on Mars like very significantly. Like, okay, so that is the important aspect. So this slide I am skipping. Already I have mentioned that there is a huge tectonic valley is there, and also like lot of volcanoes are there. So still we are not sure like what is that exact tectonic or like a petrological relationship between the formation of these larger morphological features like volcanism and that tectonic activity. Lot of studies are going on in these aspects. Okay, so now let us see what the evidence for presence of past water on Mars. Like, okay, so you can see like runoff channels are there, or dried river channels were there, identified through orbital images. Okay, so the important aspect here is that we correlate those type of features with Earth-based features. So in the case of our Earth, like we can consider this can be either due to lava flow or lava channel activity, or due to water-related activities. But later spectral studies have given some water-bearing minerals over here, and based upon that, scientists consider that these are all dried river channels. Okay, so this indicates the presence of one among the good evidence for the presence of past water on Mars. Now here, that gully formation also required water for its formation. Here you can notice that towards the crater wall, there formation of gullies are there. So that also needs water. So now here you can notice that this is one image of Mars during captured during 1999, and this is an image from same region captured during 2005. So you can notice that a white patch is there. Okay, so those indicative of like a recent ice present in the case of Mars. Yeah, see, which means that like glacial activities are still ongoing process on Mars. Then this is a like a Curiosity image. Curiosity, you know that it's a lander rover. So it has like a nicely imaged, especially the Gale crater. And here they have noticed that alluvial fans over there. So alluvial fans, you know that the formation condition, it needs that fluvial conditions for the formation of alluvial fans. Okay, so they have matched that with the Earth also. Based upon that, they concluded that this is also another evidence for the presence of past water on Mars. So another interesting aspect is that this is a 1 centimeter scale image from Mars by Curiosity mission. Okay, so here you can notice that a lot of rounded and semi-rounded fragments are there. So all of you are aware about conglomerate, okay, how conglomerates are formed. So we also learned or did that like conglomerates are formed due to water activity, and a large distance of transportation should take place in order to make it as originally angular material to rounded or semi-rounded materials. So here also in the Mars, you can notice that rounded fragments were there. Okay, so scientists proposed that, okay, so these are a sort of like a conglomerate forming mechanism. And for the formation of conglomerate also, you need water to act as a transporting agent. Another evidence. Okay, so this one I have previously shown you one video throwing a stone on a muddy condition. You can notice this one like that splashing effect. Okay, so this also indicates the presence of past water, either subsurface ice or that waterlogged regions on Mars. Like now, see, this is a Jezero crater. This is the delta-type one. Okay, so delta, you know, in which type of regions we can have formation of deltas on Earth. Like, okay, well, it formed in a water-bearing condition or water activity is essential. So this also they have mapped nicely. Okay, so I propose this as a delta, and this particular deltaic region Perseverance mission has landed and giving us some important results. Okay, so this is another evidence of presence of water in the case of Mars. Yeah. See, again, hydrogen mapping has been taken place there, and you can notice that like a different regions, especially towards the polar regions, you can notice that blue color, which is indicative of presence of water molecules in the case of Mars. Yeah, see, so these are some of the areas. So which means that again, in the case of Mars, huge volume of water in the form of water ice is there. So some other activities indicative of glaciers are also present on Mars. So you can see like polygonally fractured plains, then perennial ice cap in the polar regions. And here you can see that mixture of dusty materials with icy materials are there. That's why here it is a clean surface is there. Here it is a dusty surface is there. So a combination of glacial and Aeolian activities taking place over here. Okay, and this is a one crater on Mars, Korolev crater. Okay, so recently scientists have identified water ice from here. So you can notice that huge deposits of water ice is there. And also this is a subsurface image, like this is a synthetic aperture radar image. Here you can notice that a subsurface icy layers are there. So once towards the Noachian and Hesperian, you have noticed that huge volume of water was there. Okay, and where that water has gone. Okay, so this is some of the answers, like water might have used for formation of hydrous minerals. Some of the water is it is still preserved as permanently permafrost regions. Okay, in the subsurface region. See here, strong dust devils are there, which is indicative of Aeolian activity on Mars. You can notice that dust devils, okay, Aeolian activity. Then this is that dust scale of Mars. Here you can see this is a particular image taken place on June 17, 2001, and this is that July 17, 2001, and this is that dustiness scale. So here that red indicates that it is dusty, and this is the clear. So June it is clear Mars, and July it is it is a dusty Mars. So which indicates that dust or Aeolian activities are still a major geological process or geological agent on Mars. Okay, and that seasonal activities in the form of glaciers and that wind activities are still operating on Mars. That is, exogenic processes are taking place. So these are like wind streaks surrounding some craters are there. So the formation of these type of wind streaks also like Aeolian activities are necessary. So another evidence for Aeolian activities on Mars. Like okay, so these are some of that major research activities, or like our group is working on, like crustal dichotomy on the Mars, then volcanic aspect on Mars, like evidence of glacial processes on Mars. Like okay, so I'm because of lack of time, I'm not going into the details of that one. We also identified in some particular region, like especially that low to mid latitudinal regions of Mars, like lot of evidence for like glacial processes on Mars. Like okay. So these are some of our recent publications on Mars. We worked on glacial activity, landslides, surface composition, regional tectonics, mineralogy, etc. And this is one interesting paper came in that geomorphology recently. Here also we have proposed in that low latitudinal region, glacial activities are still taking place. Okay, so this is the last aspect of my talk, that is the planetary analog research. Okay, so I have explained that how our geology, Earth-based geology, can be used to understand various features of Moon and Mars. Some of you might be wondered like why I am using like geology of Moon or geology of Mars. It is the reason is that in order to understand those features, we have to correlate that with Earth-based features like. So we are moving to that planetary analog research and how those planetary analog research are important for this one, planetary exploration. So some of that general concepts of planetary analog research are there. It is that work that furthers an understanding through analogy and simulation. Right? Okay, and we can consider these analog sites as an intermediate step between the laboratories and real thing. We don't have to consider always that material. We can also consider that environmental characteristic, then morphological similarities, etc., like environmental characteristics, lithological similarities, morphology, etc., which duplicate the landscapes of features observed on, say, Mars or Moon. Right? Now, what are the advantages of this analog type of research? It may provide significant evidence for mechanism of formation of a particular rock unit or a mineral, a geological feature on other planets, Moon, life supporting environments, etc. And also, if we plan for a mission, especially like a geological mission is there in order to understand what are the various minerals or rocks present on particular planetary bodies, we have to calibrate those instruments. For calibration purpose also, we can use these materials like, okay, these are the chemical and spectral characteristics. Yeah, chemical and spectral characteristics of that rocks and minerals can be used to calibrate instruments, okay, in various interplanetary missions. And also, if in a particular mission, we are planning for like a rover and lander combination, like, okay, so we have to do some test bed experiments. So these geological sites can act as a potential test bed sites for present and future planetary missions also. I'll show some examples from India where like we are working on. Like, those who are not familiar with the Indian scenario. Okay, so this is that tectonic map. Okay, I'm not going into that tectonic details of that one. So we have lot of anorthosite occurrences in that diverse terrains of southern India. Okay, so one such terrain is known as that Sithampundi anorthosite complex, which is Archean in age. Like, okay, so we have like some anorthosite which is having compositional similarity to that of our Earth's moon. So that compositional similarity is based on spectra and the chemical aspects also. Okay, so like we have studied, not only we, like many groups have worked on those particular regions. So this is one field exposure of those anorthosites. Okay, so you can notice that anorthosite sample. So I consider this as a pure anorthosite sample because you can notice that these are some of the anorthosite with mafic layers are also there. Suppose if I am taking this particular portion, I can get like a pure anorthosite with any with minimum mafic phases are there. And if this particular region, I have to omit that mafic phases in order to match with like say the compositional aspect of moon. Like, so we can go for many type of studies in the field. We can measure that spectral studies, and also like in the lab we can go for spectral chemical analysis there. And then we can compare the chemical aspects, chemical features, especially the major trace, rare earth elements, etc., of those particular samples with the lunar samples also. So sometimes a close similarity with some oxides are there. Here you can notice that see a close similarity between various elements are there between that analog sample and that the other samples, lunar samples are there. Okay, so this is the approach. Okay, so we will crush powder that particular rock into several units. Okay, so we can have like clean anorthosite over here. We can have like clean mafic phases. In this particular case, we further cleaned that mafic phases and we took the chromite or chromium spinel from that one, and we now have like two units are there. One like a clean anorthosite and another one a clean chromite units are there. Now with this one, like we can have like a various combination of units which mimics the lunar surface. Okay, so we can have like a pure anorthositic region. We can have anorthosite mixed with chromite are also there. Once we know that number, we can also mix or like we can do that trial and error methods also. We can have various combination between anorthite and chromite. We can make a different mixtures like. Okay, advantage is that like using these type of mixtures for ISRO's like Chandrayaan-2 mission, like it has a lander and rover combination was so there. This is that Sittambundi anorthosite complex. They have collected nearly 500 kilogram of sample over there, and they have prepared a test bed over here. So this is that particular test bed where that rover and lander is doing some test bed experiments. So advantage is that like we can understand what are those intricacies associated with the rover wheel movement, etc. there, or what are the difficulties over there. And this is that test bed that mimics that some particular region, or especially that landing site region of moon. Okay, and also that ISRO got patent for this test bed site. And these materials, we can consider it as a lunar simulant also. Yeah. Another important aspect is that if you are planning for this one like mission, then geology can play another role also. We can create one artificial impact crater. Like so, this is one such crater in Challakere region in Karnataka area in India. Okay, so here also important aspect is you don't have to worry about that area name, etc. Important aspect here is that crater. Okay, so here crater has been created, and then rover and land this one test bed experiments have been conducted. So we can understand what will happen when rover movement is taking place over here. If some difficulties are there, we can foresee that one, and we can apply suitable correction mechanisms over there, and then place that in the mission. Okay, so this is another way in which we geologists can contribute for planetary exploration. Okay, so this is so those are regarding that lunar aspect. So another one, this is towards the southern India. We are having some region like okay, so which is entirely red in nature. I think some of the sites in Australia also have similar sites where there planetary scientists, they worked out these regions and consider it as a potential analog site. So we consider this as a Mars on Earth. Like okay, so this particular region we are having like a lot of red sand beds are there, and also some of those morphological features like gullies, etc. were there. Like okay, so we used to take students to this or like say other field areas also. We teach them in the field itself like what are that similarities. Like here you can notice that this is a gully feature, a Martian landform on Mars. Like okay, so we can have similar type of feature in this particular region. Okay, so we try to correlate that what are the features, and we will discuss how these type of features are formed over here. Then we will try to extrapolate that features or that processes to understand the formation of similar feature on say moon or Mars. Like okay, so that's another beauty of this planetary analog research. Okay, so I'll show you some close comparison. We are having that polygonal crack regions, polygonal cracks on Martian surface are there. Of course, sometimes like we cannot directly correlate, but we will see like various possibilities. Okay, or various options we can suggest. Then these are the gully regions. Okay, so here also you can notice that gully formations are there. So we can have a close comparison. We can take materials from over here. Okay, there were some interesting other features also. During this is a channel flow is there. So with channel flow, we will having accumulation of heavy minerals will be there. Similar type of features we have observed in the case of Mars also. Okay, scientists consider it as blueberries, like iron-bearing concretions were there. Okay, so like we can study in different dimensions. Other important aspect, this is another such region. The case of our Earth, we are having gypsum, that is hydrosulfate, calcium sulfate, okay, with 2 water. Okay, so this is a terrestrial site. This is on Mars. This you can notice that this is a gypsum vein, and this is a 1 centimeter scale image from Mars. You can notice that lot of gypsum veins are there here. So now advantage here is that we are having samples for here. Of course, that conditions etc. were different. We have to apply suitable correction mechanisms on also some algorithms etc. were there to understand that to perform that correction mechanism. And here in that particular gypsum, okay, you can notice that microbe colonies are there. Okay, especially along the cleavage planes. So what is that inference from these type of studies? Gypsum, it's a potential mineral which can host that microbes. Okay, so if we are aiming for any astrobiology related research on Mars, these are the potential mineral or potential sites on Mars which we can probe for, like so any microbial activities on Mars. Like okay, so these are so this is also a published paper from our group, like or students. Like so another interesting aspect is like not going into much details of that one. Another hydrosulfate. Okay, so it is present in that Ranofetch region. It is there, and towards the southern region also, we are having like a formation of jarosites are there, and this is from Mars. Several sites on Mars like a jarosite have been identified here. So in that Rio Tinto region on Spain, okay, so they also consider it as a potential analog site. This association of gypsum, jarosite, etc. were there, okay, and they have identified beautiful microbes growing in those type of minerals, jarosite, gypsum, etc. Okay, so this is another type of correlation we can do, and it has a lot of implications for that Martian studies also. So those who are interested in this type of field work, so like we can go to these areas, like we can understand that field features there itself, growth of jarosite, etc. And then we can correlate that with the satellite imageries through Mars. Okay. So then this is a carbonate one. So the Martian atmosphere, it is having a very thin atmosphere is there, but 95% of that Martian atmosphere is composed of carbon dioxide gas. But we do not have much reports of carbonates in the case of Mars previously, but recently with advancement in technology, some of that reports of carbonates are also coming up. Like, okay, so recently we have worked upon like one huge magnesite deposits in Salem region in southern India. Okay. And some other regions were also there. We have done field work, done some measurements over there. Okay, collected samples from here, bring to lab. We can do like a lot of spectral and chemical analysis of that one. And then we proposed it as a potential analog for Mars. See, serpentine magnesite association of Salem ultramafic complex as a potential analog. Like, okay, so using our geological aspects, like we can use those parameters to understand some of that formation features of Mars. Like here also we proposed how magnesite can form in a similar condition on Mars based upon these analog studies. Oh, sorry. Okay. So now the various instruments which we are using for these type of studies, like some sample preparations are there. Then we can have thin section. We can have different types of like sections can be there. Then of course that fundamental or advanced petrological microscopes are there. Then hyperspectral radiometer, which will give the spectral data of the samples. Then Raman, then FTIR. Okay, so these are that in XRD, etc. for different aspects, and this is that EPMA. Okay, placed in Physical Research Laboratory and Indian Institute of Science. Like, okay, so if we can have the quantification of elements, etc. using this one through our spectral studies, then we can correlate the spectra and chemical data, and through which we can understand how using spectra we can derive the exact composition of say some of the minerals. So those type of studies will also help for planetary exploration purposes. Like, so now coming towards the end of my talk. Okay, so notice that like this is one such region from where I am from. Okay, so like this is towards the south, we are having some sandstone beds and jarosites are there. Okay, north also we are having some different regions. Like so we have collected some of these jarosite samples from there. Okay, so we have done lot of spectral studies over there. Okay, those spectra we have used to understand the formation of similar materials on say Mars and Moon. Like, okay, so that's the beauty of this terrestrial analog studies and how we can contribute these terrestrial analogs for planetary exploration purposes. Like, so now like some of you like say if you are interested in planetary geology or planetary, some of you want to be a planetary geological aspect, what type of work we are doing. Okay, so one, like our primary source of data is that satellite imageries through various missions. Like okay, so using that satellite imageries, we can understand like we can delineate various geological features and then interpret the formation mechanism of that one. So by analyzing that this one satellite imageries of planets, then moons, asteroids, and comets, we can begin understanding their origin and evolution. Now, if you are having that meteorites or terrestrial analog materials are there, okay, so we can have like work with actual specimens. So actual specimens are here in the sense that if you are having in situ samples, if you are having meteorites, and if you are having that terrestrial analog samples, like, okay, so we can do a lot of chemical spectral analysis, etc., and we can come up with some meaningful conclusion or meaningful inferences regarding that formation mechanisms, etc., or we can use those materials to calibrate the instruments placed in various missions also. So these are the main role of planetary scientists. Like, okay, so various space agencies are there and lot of global opportunities are there because a lot of interesting missions are coming up from various space agencies where we geologists can contribute a lot, like which includes like Indian Space Research Organization, NASA, then JAXA is there, JPL, then USGS, then German Space Agency, European Space Agency, Japan Space Agency. Recently, very good publication from Japan Space Agency came, especially on finding of pure anorthosite from lunar surface. That came recently only, I think, few weeks back. So these are the various space agencies working on like various aspects this one. And also you students, like mostly your students, some of you are interested, like you can attend like a major conferences, like, okay, like in India, we are having Indian Planetary Science conferences are there, same as that one, like a JPGU conference by Japan, it's there, then AGU, then EGU, EPSC, LPSC, etc. are there. So most important aspect for you students, like youngsters, you please try to establish contacts with renowned scientists in this particular field. Okay, not only in this particular field, that other geology fields also, you interact with them continuously. Okay, and if you are having enthusiasm, motivation, imagination, then hard working capacity, you should be able to come up with your own ideas and know how to pursue them to completion. Okay, so coming to conclusion, these are the future challenges for you. Okay, so though we know like a lot of aspects on mineralogy, surface aspects, morphology, etc. So our knowledge is very limited in the sense that through missions, like, okay, so whatever data we are getting is sometimes it will be huge volume, but interpretation aspect, it will be minimum only. Some other cases like that probing in a smaller location, but we have to focus on larger regions, like, but still geologists or geoscientists, like we can contribute on mineralogy, petrology, then surface morphology, interior studies, geophysical experiments like gravity, internal studies, seismic studies, etc. We can also contribute in experimental setup, instrument developments, etc. Then sample return missions, in situ exploration. Suppose if you are taking Moon or Mars, like more and more water resources, volcanism, space weathering processes, etc. Then robotic and human explorations are there. So like many missions are there for you youngsters. Okay, like to Mars, Moon, Venus, asteroids, etc. are there. Like okay, so these are the persons have helped me to prepare this presentation, and thank you very much. I hope I have introduced some of that geological concepts of Moon and Mars, and also how we can use terrestrial analogs, okay, used for planetary exploration also. So thank you very much.
Okay, thank you, Professor Rajesh, for an enlightening talk on the various aspects of let's say lunar and Martian geology. So it was very, very useful and exciting topic even for me. So I suppose there were some questions regarding in the chat. It was a couple of them, and there are something more coming up. So first one was about how is now plate tectonics a consequence of little or no atmosphere? I suppose it was from Aman Sahu. Do you have any comment on it, Rajesh?
Yeah. Sorry.
It was at how is
the query was plate tectonics and the relation to atmosphere.
Yes, that is true.
So in the case of like our Earth, like, okay, so plate tectonics, we consider it as a sort of recycling process. Okay, so because of plate motions, like we can have like subduction processes can take place, then divergence processes, etc. Okay, so it can create a formation of various volcanism, various tectonic activities, etc. Say, for example, if a volcanic activity is taking place, what will happen? It will release lot of gaseous phases to our atmosphere, right? Okay, and since our atmosphere is also dynamic in nature, like geologic agents were there, etc. What will happen? Some of these gaseous phases, like it will also be part of various reactions there. Okay, and especially if you are taking like a carbon dioxide, it reacts with water over there. You can have formation of carbonic acid, and when it comes interact with the limestones, something like a further carbonation process can also take place. Okay, and we can have formation of some carbonate rocks like and some of these sediments or sedimentary rocks with carbonates, etc., can be formed. Okay, so they will also take part in further subduction processes. Okay, so that there will be a cycle chain and it will accelerate the plate tectonic processes also to some extent, but still there is not a direct relationship in there. Another example I will say you the case of Venus. Okay, so Venus also, all these volcanic activity, etc., were very vigorous than Earth. Like it also releases lot of this one gaseous phases to the atmosphere, but there is no plate tectonic processes over there. Because of that, what happened, all these gaseous phases, they have been stick to the atmosphere only. So a very thick atmosphere has been formed with the carbon dioxide, okay, which do not have any interaction towards the deeper side. The consequence is that Venus, towards the earlier stage, it received heat from internally, and this carbon dioxide, okay, global warming effect will be there much more than our Earth. Like what will happen, the surface also receive heat from atmosphere, and because of these two heat source from the deeper side and heat source from the atmosphere, always the surface of that Venus, it cannot act as a single solid unit like our lithosphere. Okay, so because of that, plate motions won't take place in the case of Venus. Instead, we call it as plate tectonics. Okay, so this will crumble, go towards the deeper side. It will come out in the form of melt. But subsequently, what happened? Like a lot of like volcanic activities were there, but no plate tectonic processes were there. Okay, so that's a case of that plate tectonic and atmospheric interaction in the case of two planetary bodies, one between Earth, one with Earth, and another the case of Venus. Yeah.
Excellent. That is very good explanation from your side. So I'll just introduce Charlie Hughes, who would like to ask you about. There were two questions. I would pick up. What sort of minerals are formed within impact melts? That is his second question. Actually, he wanted to ask about the rill. Does the rill process still happen today? Those two are where Charlie Hughes questions. So can you?
Okay. So yeah. Okay. So that process, like it can happen, but we have to confirm that volcanic activity is taking place. Like okay, so till recently we considered that, especially in the case of Moon, we consider it as a dead planet. Okay, but recent planetary mission data, it says that it was active till 100 million years ago, but some of those studies says that till 2 million years we had evidence for volcanic activity. Say suppose if volcanic activity is taking place and the lava flow is overflowing, or like a volcanic activity, same as our like a basaltic flow is taking place, we can have formation of lava tubes or rills on any planetary surface. The most important aspect is that we should have internal heat, we should have formation of volcanism, and we should have like enough melt flow or lava flow to have formation of the rills. Like so that is one answer. But if we are considering that the rate of rill formation between past and recently, like we cannot have a correlation, because now that formation of will be like in the extremely like a minimum rate, but in the past it might have formed like a larger pace. Okay, so that's the answer to the first question. Like then what sort of minerals are formed within impact melts? Like okay, so that is actually a very question. Of course, like some general answers are that tectates can be formed. It is that fused silica. Okay, so my answer to this question is that it depends upon what is the composition of the impactor and what is the composition of that target material. Okay, so depending upon that one, like fusion will take place, fusion, melting, etc. can take place, and depending upon the composition of that, we can have formation of different impact minerals. Sometimes high pressure minerals like coesite, then high temperature minerals like cristobalite, etc. are formed within the impact melts. Okay. Again, some cases like in that impact melts, diamonds have been identified. Suppose that particular region is a carbonaceous terrain, and because of this high pressure, there is a variety of diamond known as lone stylite. Like okay, so that will form. That is of course a micro diamond. Okay, so that can also be formed associated with impact activity or impact melts. So the contributor for the mineral formation to that impact melts are, that is from that impactor composition and also from that crust under which it is undergoing melting. Right? Okay, so that's the answer for that second question.
Yeah, that's great. Thank you. There are a few more questions. I will pick up one each from Sakshi Bansal. He wants to know about the reasons for liquid water disappeared from Mars. What are the
reasons for sorry
for liquid water disappeared from
yes.
Mars?
Yes. Okay, so like planetary scientists considered that towards that earlier stage, okay, water was there. That's why like they got in a terrain, okay, in an older terrain, lot of abundance of say clay, then hydrosulfates, etc. were there. Okay, so to answer this particular question, like we have to understand how water has been formed over there and how water has been gone over there. Okay, so previously like Mars has a very thick atmosphere. That is during its earlier stages of its evolution, and the conditions of Earth and Mars were more or less similar. Okay, so at that time, like a lot of water there, and also that the primitive volcanic material of Mars was basalt. You all know that like what will happen when basalt interact with water. Okay, you can have formation of clays, and if conditions are favorable, you can have like say formation of other minerals also. Okay, so then what happened with the course of time, Mars loses its capability to hold that thick water atmosphere. Okay, so it has been wiped off, and because of that one, what happened like water not stay in the surface of Mars. Like so various possibilities are there. Some of this water have been utilized for the formation of minerals or rocks that require water for its formation. Some other it might have escaped to space. Okay, some other like it is still preserved as permanently permafrost materials. Okay, towards the deep side. The evidence for that is like recent studies, especially based on synthetic aperture radar studies. Scientists have come up with a lot of regions of on Mars, like okay, with that subsurface ice very well preserved. Okay, so if you are like quantifying that one, like even that is a huge quantity, that one. So these are some of the answers, like one like water has been lost to atmosphere, then second like it has been utilized for formation of minerals or rocks that requires water for its formation, and third this process it is still preserved as this one frozen material towards the subsurface Mars.
Okay, I think we are getting out of time, but still, can you quickly answer about Charlie Hughes one more question on why there are less number of craters in the on the visible side of Moon? Because is it because of shielding by Earth?
Yeah, that is an interesting question. Like okay, so the question is why there are less number of craters. Like I think you might have seen this one, like a formation of that darker regions. Like okay, so that darker regions, it is actually like suppose you assume that there were no darker regions there. Okay, so what will be the scenario? Only those impact craters were there. So in that case, of course, I'm not sure about the numbers, but still we can say that like large number of impact craters were there in the near side and the far side also there. But towards the near side, the crustal thickness is less when compared to far side. So during that impact cratering process, that shock waves, it can penetrate towards the deeper side, say only up to 50 kilometer, something like, or in between also, wherever it is having melt pockets in a shallow level. What happened? It has migrated through those fractures and occupied the craters. So what happened? The craters got obliterated, and in that imageries, etc., we cannot see those craters. Instead, that crater got filled up with these basaltic materials and has been masked off. Like okay, so that is one answer. So another one, there is a effect of like a tidal attraction towards the Earth also. Like okay, again, like all these iron bearing materials, it has been shown some attraction towards the Earth facing side only. So that is why like more these marine materials can be present towards the Earth facing side, and if more marine materials are there, like they will initially occupy these craters and then they mask up the craters. That is the main reason why like we are having less number of craters towards the near side and more number of craters to the far side. So in order to reach to the partially molten materials in the far side crustal regions, like the shock waves or that fractures should reach up larger depths, like, okay. So this is the one answer.